All right, guys, I think we'll get started because it's 5 o'clock and there's more questions this week to get through, and they're a little bit more involved than last, what was it, fortnight? Last fortnight. How often do you hear that? Before we start, I just wanted to bring up a couple of things. So last time there was a couple of things I thought about when I went home, deep in my meditations as I am. And one thing was that there was quite a bit of talking last week, and I know that people want to talk or in person, hurrah, it's really nice. But it's quite distracting for me as a teacher to teach you when I can hear people talking. It just breaks my flow. And also, some people get distracted by it as well when they're listening. So just be considerate and try not to talk. And if you do find it the imperative to talk, try and keep it to a whisper if you can, please. Thank you. Second thing was that there were lots of people answering questions last week. Fantastic. That's what we like, and I love it when you guys do. But can we get hands up this time, please? Just give people that don't usually answer a bit more of a chance if they feel so inclined to answer. You see what I mean? It's just hands up and I'll call on you. Just a bit of a, I don't know, bookkeeping, I suppose. There was also a question last week I got from the front, which I thought was interesting to briefly explore for like a minute. Do you guys remember the question of the shaft that was rotating and it got the shear forces on it over the viscous forces on it over its area? Do you guys remember that question? I got two questions on that. Number one was, because I drew it with the arrows facing that way to demonstrate the rotation when I drew the surface area force, someone asked, does that generate a couple? Should the force be doubled? The answer to that question is no, because in doing the, if you remember, we divided or times, one of the two, whatever, we took the whole area's force and converted that to our tangential force. So that means that all those tiny little vectors I drew on that shaft were all converted into a single force. So no, it doesn't generate a couple. The second thing was when we were talking about torque. Now, if any of you know about vectors and how torque is calculated using vectors, it's done using the cross product. And the cross product defines, if you take these two vectors and take the cross product of them, it defines a normal vector to that, and that would be your torque. But that doesn't make much sense when we're talking about rotations. So what are we talking? What's going on there? Well, essentially, the cross product is a bit weird and doesn't really demonstrate rotations very intuitively. So just for all those that care, because I got a question about it, if you use the cross product, it generates a normal vector. That normal vector defines what's called the torque direction, and you use the right-hand rule to demonstrate which way the torque is rotating. So I just thought that would clear something up if anyone has been thinking about, has been stressing their minds over the last 2 weeks about, oh, but what about vectors, though? I'm sure you all do that. Okay, so now that's out the way, let's start with the tutorial. So I assume you guys have done have tackled it, so, because these questions, again, they're those kind of questions that are just arduous to go through because they're long, and it's a lot of chaining. I think of these questions, these hydrostatic ones, especially ones like this where we've got the manometers and they're all chained up as pressure chains. That's essentially what you're looking at. You're analyzing the chain from one end to the other and just understanding that the pressure converts the whole way through. Yes? An angle? Well, we do a question that does involve I think there is one that does involve a manometer angle, and the kind of way it would. You would just use a different, this one has an angle. You would just use a different calculation for the volume, I think, pretty much, because the pressure of the air is without direction. So you just use a different, you just obviously it would tilt and create a parallelogram of volume, or like a slanted cylinder, and you just calculate the volume of that to get your pressure, right? Yeah? Right, so these pressure chains, let's have a go at one of them. Let's get started. So we want to find the pressure in that little vessel at the far end, A, and we know that we're given the atmospheric pressure and what substances exist in these manometer tubes and the U-bends, and how much there is given the height, right? So we're going to flow through this using some hydrostatics. So the first bit to do is to start at D, since it's the beginning, and it's open to atmosphere. So the pressure there, the pressure at D, we're going to just start with step 1. Pressure at D is just the pressure of the atmosphere. I'm going to put at M, which is atmospheric pressure. I'm going to work through this algebraically, and we'll fill in numbers later because it gives a better understanding and doesn't lose kind of the intuition in the numbers. So next we move to this next point, which is 25 centimeters of water down. So that means we've got to use the 25 centimeters of water in the basic hydrostatics equation and add that on. So step 2, which is at the pressure at CC, so we're just chaining along on these, is the pressure at D, so we've got that air pressure coming down, and then we're going to add on the density of the water, and then the gravity, classic gravity comes in, and the height of that, which is, oh no, I said I was going to do it algebraically, and by golly I will. That's the height, I guess CC, I guess. So we'll put numbers in for height, because it doesn't really matter. You can see them on the diagram, and I think that'll be less confusing actually. So that's 25 centimeters. So all this is saying is we've got 25 centimeters of this dense water, and if that much water is sitting above something, due to gravity, which is why G comes into it, you get this much pressure, okay? So then we move around the bend. Now the bend kind of balances itself out, which is quite nice. So then we move around to C dash, C whatever, C dash, C apostrophe, I don't really know. And it's just the same as C dash dash because, I mean, if you think about, you see where the line is, the U bend kind of balances out that pressure and just keeps it constant. So we end up at C, we end up with the same pressure. So we can just say that this equals this, and that's equal to, if you remember, PD rho water, G 0.25. Cool. Now point C4. Oops, let's put my pencil. Let me just. So point 4. Oh, we haven't got the points on here. Sorry. I realize I've been talking about C's and stuff. That's because I'm looking at the solution sheet for my things, and that's got them labeled. So I apologize if that's horrendously confusing. Let me just. Let me see if I can show you this in. No, will that take ages? Let me get that up instead because I think that saves me drawing out the diagram. Prepared to see behind the curtain. Cool. And then open that. And then we'll quick everybody write it down. All right, there you go. So now you can see what I was on about with the A's and the B's and the D's. Okay. So sorry about that. I didn't realize that wasn't on the actual sheet. So we're here, just above the mercury, right, where that air is. And we're going to, the pressure of the air, yep. Where are we? Lost my flow. Column of air. Yeah, so there's a column of air there that connects the two, but air has such a low density compared to mercury and water that essentially we can just neglect it. And we say that at that point that PC, this point where the mercury is at the top, is equal to the same as C dash. So you can think of air as like a transmitter of pressure between the two, right? Because its density is so low, it doesn't contribute much. It just sort of maintains that balance, right? So yeah, that's just equal to this pressure. So then we've got point B dash, which is below 30 centimeters of mercury. Now, so when we're talking about this point, it's contributing to the pressure again in A. So this whole point we're trying to get to A, right? So this mercury is also pressing down on it. So that means we can say that the pressure at B apostrophe is equal to PC apostrophe plus this pressure of the pressure caused by the mercury. So Hg. G, and then the H there, which is 30 centimeters, 0.3. So again, that's the same hydrostatics equation we used here. And again, all it's saying is that you've got this much mercury, and it's this tall, so how much gravity does that, well, and it's under the influence of gravity, so it contributes this much pressure, okay? Again, we've got another U-bend, so nothing happens, it balances out. And we move through to point B, 6, which is point B. Pressure at B, right. So it's at the same level, so that means that PB is equal to PB apostrophe. Cool, that's sound. Part 7, which is the point. Yeah, so B is also below this 70 centimeter column of water, right? So we can write that PB is also, oops, whoa, what the heck? That's a beta. PB is equal to the pressure at A, cool, that's what we wanted, so we're getting closer, plus that little bit of water, right? So it's saying that the mercury and all that chain before it is balancing out with the pressure in A and the water that's coming down on it. That's what we're writing here. So I'm going to write PB is equal to the rho of water, G, and then 0.7. And then remember that that's equal to this up here, which is PC dash plus rho HG, G 0.3, right? So that's what I was talking about with that balance. So then all we need to do from this is rearrange this part of the equation to get the pressure A, right? So we write pressure of the atmosphere plus that pressure caused by that original water column, which is 0.25, plus that little bit of mercury, which is that bit, G 0.3, and then minus that little bit of water, because it's contributing the other way, G 0.7. Is that correct? That is correct. That's what the lecture man tells me. So PA, once we fill in all the numbers. Now, does anyone, so this is we're given the specific gravity of mercury, and as if anyone here was last week, I don't know what that means. So I've written it down this time, and I hope I've got it right. So when we put in, so we actually convert that to the density of mercury by timesing it by the density of water, which gives 13,560 kilograms cubed, because it's important to do your units. And when we fill in all those numbers, which I'm not going to bother doing, can anyone tell me the pressure of atmosphere? Can anyone tell me that? Hand up, bro. Yes. Yeah, sure. Yeah, so yes, but you can estimate it to be like, you know, a bar if you're really feeling engineering and want to go for just the base estimate, right? So that gives us 35.5. I'm not going to bother filling in. You guys can use calculators, I hope. Actually, to be honest, we don't. What this is not actually the full answer, right? This would be plus the pressure of atmosphere if we were talking about absolute pressure, because we're not asked for either or, but we can talk about pressure in two terms: one in terms of absolute pressure and one in terms of gauge pressure. So this here is the absolute pressure. If I remove this value here is the gauge pressure. So gauge pressure talks about the pressure relative to atmosphere, whereas absolute pressure talks about the full-on from vacuum pressure, right? I hope that's clear. Okay, so next question. I'm going to go back to the actual thing so you can't see the answers. Wait, what? 2. Ah, yes, I like this question. Question 2. We got some sediment and it's settling. Oh, that's nice. Look at it curl up. It's like a small cat. And we're told that there's a surface and Y increases as we go deeper into whatever it is, the substance. I think it's water. Is it water? Brackish water. Yummy. So you can say that it gets denser as we go down. And we're given that density gradient. Now remember last time we talked about like velocity gradients? It's just an equation that tells us how the density of the sediment changes as we move down that depth. So that is given to us as 1,000, 1 plus 0.2y. So again, it's just one of those lovely equations that tells us how it changes. What else are we given? Well, y is the depth below the free surface. What's your gauge pressure? So this is where we're talking about gauge pressure. So when you're doing exams or doing coursework, be really careful that you know what type of pressure they want, because they will try and trip you up with it, right? And usually want you to move around it. So make sure you, like, when you're reading through the question, underline gauge or underline absolute. If they don't specify, go for gauge because it's fancier. Yeah, so 1 meter below. So we're going to a y of 1 meter. Now, just to be clear here, y is increasing as we're going down in the positive. So we're calling this a positive increase going downwards. In fact, I'm going to write that so it's clear. So to do this question, we need to look at the fundamental form of the hydrostatics equation, right? That's a derivative, sorry, given by, I want to say it's P. So this is the change in pressure with the change in some height underwater or some fluid, and then minus rho g, right? But because we're talking about y increasing as we're going down the depth, down into the water, we're going to write that z is equal to minus y, and therefore this equation becomes this. Right, that negative is just removed, and it makes it a little nicer to play with. Okay, so we'll call this equation 1. So what we're going to do is we want to figure out what it's like to be here at 1 meter down, right? So we'll call this 1 meter down. What is it like down there? How does it feel? To do that, what we're going to do is we're going to essentially add up all the little chunks of, all the little strips of water above that thing on the way down, right? So we can do that using integration. That's essentially what integration is. If you have a function, you add up, you sum all the tiny little bits of it, and then it tells you what's going on with that function up until that point, right? And how much you've accumulated almost. So if we move down, we can say, what's pressure here, what's pressure here, pressure here, pressure here. Yes?
I don't understand why it comes out negative if y is positive.
Well, think about if this y is coming in here, sorry, if this y is going in here, there's a negative here, right? That negative comes with it, so that will go there.
But I thought you said that y goes down and y is positive.
I did say that. Good point. Because the way you talk about it when you talk about hydrostatics is from the bottom up, right? So I think if you're saying Z is increasing that way, then no, that doesn't make sense either. What do you have to call out on the nicky picky bits? Why would that make us? Why would that make a difference? Yeah.
I ended up with dp by dy equals minus rho g.
Yeah.
And I ended up with a negative answer.
Yeah.
Because of course graph. So what you're doing must be right.
Yeah, I guess so. When I looked at this bit, I just was like, when I read it earlier on the solutions, I was just kind of like, oh yeah, of course, well that makes perfect sense. But now that you're asking me why it makes perfect sense, I have no clue. Can you trust me on this for now and let me think about it, and maybe I'll get back to you next week on it. Just trust me on it for now so we can just continue going. But yeah, like your friend says, it does make the sense when you get down to it. It probably won't make that much of a difference because essentially it's just unitary. So like you're just going to have a minus sign. That's all you're going to get. But does it make physical sense? So yeah, just trust me on that for now, and I'll get back to you guys about why that is next week. I'll have a think about it after. Okay. Yeah. So what we're doing is we're adding up all those little bits on the way down, and we're going to integrate the equation. So we can write that the change in pressure, that's a delta, the change in pressure between the free surface is equal to the integral between this, why is it called L? Let's call it H. So this is H, right? This is H here. H and 0, saying basically we're going to integrate between the top and the bottom, right? Or the 1 meter where we're going to. And we're going to just slam in the hydrostatics equation there. And then we're going to do that with respect to y. So we're moving through little chunks of y. That's what that integral says, okay? It says add up, the integral sign is actually an S from the word sum. So that's basically saying add up all the little bits of rho g for every little bit of y between those two values, okay? So then we do that equation. We just substitute in, we substitute in our lovely equation for density up here, which we will call equation 0 because I've already called something equation 1. And yeah, we put that in, so H0, and then we've got 1,000, 1 plus 0.2y, and then I'm going to put the g in here, and that's with respect to y, okay? So then we do that integral. Does anyone, let me just take the constants out because I can't bother doing that. Does anyone know what this bit integrates to when we do it with respect to y? Can anyone tell me? Yeah, go on, mate. Yeah, that's correct. The reason that is because, just so everyone's clear on how we got there, when you integrate, remember you're kind of doing the opposite of differentiation. So this here would usually disappear in differentiation, but because we're going backwards, we need to find what when differentiated becomes 1, which is just y, right? and then we get 0.2 y squared, and then remember the power comes down to the bottom, so we get this, and this just becomes, this just goes to 0.1, right? Is everyone okay with that integration? Yep, cool. Right, so then we're going to go h and 0, excellent. And then we're going to fill in those values, which becomes 1000 g 1 plus 0.11, because we're going to 1 meter, so 1 squared is 1. And that gives us 1000 g 1.1, which equals 10.8 kPa, right? And that is gauge pressure, because we're not including the pressure of the atmosphere coming down from the top. All we're talking about is the pressure from the sediment as we move down the thing. Is everyone okay with that, with what we've done there? Does anyone have any questions on it? Nope? Sure? We're going to do another question that's kind of like this later. So if you have, I think, if you have questions about it, they might be answered there. But just when you're doing a question like this, just remember, what is integration saying, right? It's saying just add up all those little bits up until the point you're looking at, and given a function, we can do that using integration. That's how integration works. Yes. Where are you looking? Yeah. Do you mean when I was doing the before I even did the integration? Because it would get rid of the integration, the part. Oh wait, would it? 0.2 y and then put 1 in. Why didn't I do that? Would that make a difference? Put y in there, 1 and then plus 1, 0.2 plus 1, 1.2, and then put in, and the differential was 1.2 times y, and then that would be 1. It makes a difference. Don't do that. It makes a difference. If you were to do, so if we went from here, where I've done 1 plus 0.2y, and we substitute in 1, then we get 1.2 up there, wouldn't we, dy, okay? And then when you do this integration, it wouldn't look like that. What you'd have is 1.2y. And then when you put 1 in, this would be 1.2, okay? So it makes a difference to the final answer. In this case, it's quite nice because our numbers are quite small, but in another sense, if you were using larger numbers and not so well defined and given to you by a nice tutorial man, they might come out and blow your answer up, right? So just do the integration first. General rule of thumb for doing anything with maths is do the algebra first so you can understand what you're doing, and then put numbers in last, like at the end, unless you really can't avoid it, or if something is just horrible to notate, okay? I don't know why mathematically it makes a difference. I can't really tell you. I'm quite interested to know why, but yeah, just do the integration first and then put your numbers in, okay? Right. Oh, that's another thing to think about. You guys ask such good questions. I always like on the walk home. I'm like, what did it mean? What was going on? Like, why did that happen? Why was it like this? And they're such good questions. Right. So that's that question. We got the answer. Nice one, guys. So I used to hate these questions as an undergraduate. I don't know why. I just kind of think this pot looks really like up its own arse, to be honest. But that's just I always used to. You open your exam and it's the first one. You're like, oh, it's you again. Like. So this is a manometer. It's filled with oil of a specific gravity, Sg, and this is question 3. Sg equals 0.85. So remember that's the density of whatever the fuck it is over water. And the cistern is initially open to the atmosphere. How lovely. A pressure line is then connected that creates a gauge pressure. Remember, being specific here, it's a gauge pressure of 500 pascals. So I don't really want to draw this, so I'm going to draw a really rubbish drawing and just, it looks like this kind of. And we've got 500 pascals going in there, and that's gauge pressure, so that's on top of the pressure of air. And the oil surface is displaced, and so this surface, oh god, this is going to look awful, was there, and it moves to there, right? And what that does is it forces the oil up the little spout, right? By what is we're told is 20 centimeters. 20 centimeters, and we're going to call that D. And we've got, this is 5 mil diameter. 5 mil. This is displaced, wait a second. This is in the tube. In the tube is displaced 20 millimeters. Right. Determine the manometer angle. Very well. Yes. I remember this question. You bloody pot. Pressure B. Okie dokie. Let's pressure B, pressure B, pressure C, pressure B, pressure C. Sorry, I'm just making sure I've got these ones right. Like I say, these ones are not my favourite, so just making sure I'm getting it right for you guys. So the first thing we're going to do is put some labels on this back. We're asked to find out what this angle here is. Okay, that's that alpha there, because in knowing that we can find that out by the pressure and how much it climbs the tube as a result of that pressure. So the first thing to do is put some labels on things. We'll call this point here where the oil in the tube started, point B, and we'll call this area here, we'll just call this A, this is an area, area A, and we'll call this point, this here C. Okay, so first things first, we want to find the pressure at B, right? The pressure at B. And that is PB. And again, this is our favorite friend, the hydrostatics equation, rho GH. Now, H is in this equation, my drawing is so rubbish, so sorry, but this arrow should be here. H is this height here, so we're dealing with a triangle, right? So we can also write H as rho G, and then it's going to be the D, this distance here, the hypotenuse, and then sine of that angle. So that's just trigonometry, okay? I hope everyone's okay with that. So we've set up our equation for the pressure at B, and then we're going to use the pressure at this point C from the displacement to get that pressure at B. So the pressure at C. Where's my notes? There they are. So we're going to say that the pressure at C is equal to rho of the oil, G times, and we'll call this little bit here, I'm going to call that delta H, because it's the change in height, delta H. And then that's plus the pressure at B, right? So basically what we're saying here is this oil here, there's that much, and that's weighing on this point, that's pushing down into the manometer. And we've also got this 500 PA pressure pushing this down to C. So those are balanced now, so we can say that the pressure at C is equal to the two of these. Rho G, yeah, so we just write that out, rho G D sine alpha, and then plus this bit, rho G delta H. Since the liquid oil is incompressible, yeah, side pipe equal to fluid. Yeah, so we're dealing with an incompressible fluid, right, because it's an oil. So the fluid which moves into the side pipe equals the fluid lost from the chamber, okay? So there's no change in density, so if everything moves, it has to conserve mass, right? So we can say that this bit inside of this tube that's moved from B is equal to this bit here. So we can write A delta H. So basically I'm just, because this manometer's of area A, and there's kind of like a cylinder. You can't really see it in my drawing, but you can definitely see it here in this drawing. There's a circle here, and there's a height that has been displaced. So we're doing the area of a cylinder. So the area of this manometer times the H gives us the volume of the displaced fluid, and we're saying that that's equal to the tube's area, which is just simply A, which is this area here, times D, the amount it's moved, right? Because if you've got a slanted cylinder, because it's slanted like this, if you were just bend it like that, it would be the same, right? So really, it doesn't really matter that it's angled. The area D thing still works here to get the volume. So then we can write that the change in H, which we need for this equation here, the change in H is equal to the ratio of the areas times D. So that's just rearranging this equation here. So therefore, wait a sec, let me read this. Yes, that's correct, isn't it? So now we've got both of these in terms of D. So we've got D sine alpha, and now we've got delta H in terms of D as well. So we can rewrite this equation as, let me bring that down, rho G, and then it will be D outside actually, sine that, and then it's A over A. Okay, so is everyone happy how we got there? Just substitute in this delta H with this, okay, which we found by conservation of mass from an incompressible fluid. We happy? Are we all following? Yeah? Cool. Okay, so we've got the areas of these. There's a 1 centimeter diameter there and a 5 mil diameter there, which if you put the numbers into your classic, it's pi r squared, right? You know when your brain just goes boop, is it pi r squared for the area of stuff? Thank you. I'm supposed to be teaching things. They put me in charge. Pi r squared for your area, right? If you do, that's the same for this one, I guess. Well, call that capital R. You know, you get the gist, right? You put those both in, and I'm not going to bother doing it, but you get 1 over 2 squared, right? Which is 4. 1 over 4. Why did he write it like that? 1 over 4. 1 over 4 equals 1 over 4. Statement of the century. Yeah, and then we just substitute in the numbers. So let me do that just to demonstrate what we're talking about. So I'm going to rewrite this equation here. PC equals rho G D sine of alpha plus 1 over 4, because we calculate that now. Okay, so, and this is what we want, right? So let's put the numbers in. So 500 is PC. That's because that's what we were told is displacing that oil downwards. You can't see when my hand's in the way, but it's displacing that oil downwards. Rho is this thing here. So we've got what, sort of 850. And then G is the classic G, 9.81. Always use 9.81. People that use 10 can, like, you know, just get back in the sea. D is 0.2 because the fluid's creeped up the tube, 0.2. And then we've got this sine alpha 1 over 4. So now we need to rearrange that equation. So we need to do it like, how are we going to do it? How are we going to do it? How are we going to do it? We can expand the brackets, do that. Let's divide that. So 500 divided by 850, and 9.81, 0.2, and then minus 1 over 4. They've done it a really interesting way. I'm not really sure why they've done it like that, but they have. And then sine minus 1, that bad boy. And that should give you, if I've done the maths right, 2.85 degrees. Okay? Yes?
In some steps, you have the outside brackets. Shouldn't be inside the brackets next to the A over lowercase a side?
Nah, so you can see here that the delta H is equal to A over AD, right? Yeah, so when I put this into this equation up here, I've just taken that D outside so that the two are there, because there's D in this, and there's, there's a D in this, right?
It's actually my glasses.
Okay. Happy with that question? I hate manometers so much. Yes? Oh, it's just pi r squared. That's all it is. It's just A equals pi r squared, and that's like A equals pi r squared for the other area. So that's the, look on that screen. That's this area. That's capital R, I suppose, or like that. Well, that would be capital R from there to there, and then this would be little r on this one, right? So I was trying to just say that they're the areas of the two bits of the manometer. Yeah.
So why is
A times delta H equals AD. So that was because we've got an incompressible fluid, which means that any fluid that moves down from the top of the larger reservoir is equal to the fluid moving up the tube, right? So that's just that's equating the volumes of the two, right? So we're saying the amount that moved up the tube is the amount that was pushed down by the pressure. Okay. Any more questions on that one, or can I move on? No? Okay, let's move on. Okay. I've got 2 question 5s for some reason. That's interesting. Bang! Question 4 is another manometer. Hurrah. This one's got mercury in it. Ooh, ooh. That's what it looks like. Wow, artistic. So it's moving H meters when from the reservoir, when the pressure in the tank is 150. I'm just going to draw it as like, I'm not going to draw it solid. The tank looks like this. And this is 150 kPa absolute. So they're specifying again here. So you've got to make sure that you know, this is just, like this will be the lecturer saying, make sure you know which one you're working in. If the absolute pressure in the tank, is increased by 50%, what will the percentage increase in HB? So does anyone know, well wait, let me just see if it's not written there. Absolute pressure refers to the pressure above absolute zero. Yes, okay. Does anyone know why this question is kind of tricky? Can anyone tell me? Yes, mate.
Can't see the difference between mercury and
that is the fault of the projector and not the not the question. Anyone else know why? That's not a big deal. So basically, manometers measure gauge pressure, right? They don't measure absolute pressure. So this is a question that is literally about that thing I was saying to you about knowing which one you're in and why you need to know which one you're in, because manometers do not measure absolute, they measure gauge. So in order to do this question, we're going to need to move between the two a little bit. So we'll write our hydrostatics equation like this. So we've got the pressure of the atmosphere, which is the pressure coming down like this. I'm going to draw it as like a 2-arrow thing. This is the pressure of the atmosphere, and if you think about it, the pressure coming from here, from the mercury in the reservoir. So we write pressure of the atmosphere plus rho GH equals 150 kPa. I'm just going to write 150 because we're going to work in kPa, right? So again, this is saying, like, because we were told that this bit, the 100 we were told this bit's absolute. We know that it's the pressure of atmosphere plus whatever the contribution is from the tank. Tank? Yeah, the tank. No? Yeah, maybe. Yeah. Rho GH. Rho GH is the gauge pressure, right? And this whole thing is our absolute pressure, and we're told that we're given the absolute pressure. So if we take PA to be 100 kPa, we'll just use the estimate thing. We end up with rho GH is equal to 50 kPa, right? And we're told that the pressure tank is why is it like that then? Right, yeah. Ugh. Oh, right, yeah. I got it. So this is our gauge pressure in the tank currently, right? And we're told that the absolute pressure increases by 50%, right? So we need to write. So we're taking this again. So it's 1 bar, which I'm just going to plus the rho G, and then the H nu, which is how high the mercury nanometer rises when we increase that pressure. H nu, this is H old, and then I guess H nu will be like up here somewhere. Right, and that is equal to 1.5 because we're doing a 50% increase times 150. Okay, and again, I'm just going to work in kPa because it's easier here. So then, what we can write, we'll call this equation 1, call this equation 2, and we want to know the percentage increase in H. Okay, that's what we're trying to look for. Should have said that at the beginning. My bad. Percentage increase in H. So we've got this tank, it's got pressure in it, we increase that pressure, and the height of the mercury rises, and we want to know the percentage of that height rise. Okay, so to clarify, we've understood that this is absolute pressure, so we've got a gauge pressure here, and we know what the gauge pressure is, there it is, and we've said that this increases by 50%, so that's 50% increase, and then what we're going to do to find the difference is we're just going to do equation 1 minus equation 2. So we end up with I broke my pencil. Rho G and then H nu minus H. So this, as you can see here, that these two would just cancel out in a negation, and these two would be taken away from each other, right? I hope that's clear. Wait, what? Why is that way round? That definitely shouldn't be that way around. No, it's 2 minus 1. I think there's a mistake in the solution sheet. 2 minus 1. Right, just to be clear, we're taking the new one from the old one. Right, sorry for that. That's you can blame the lecturer for that one. And this equals 1.5 times 150 minus 150, which gives us 75 kPa. But I'm not writing kPa's. I'll write it here so we're clear. kPa, that's K. Okay. So in order to find the this ratio here, wait, what? Do I need my T? Okay, yeah. So we want to find what this difference is, so we can find out the 75 kPa, so we can find out the percentage increase, right? So we're looking at that divided by that. That's going to give us. We've done this a really fancy way, and I did not do it this way. That's because we're not actually given any values, is it? I feel I'm not doing too well today. Sorry, guys. I'm trying my best. It's just, you know, when you do stuff and you just look at it and then you go, yeah, I've got that. And then you go in and you go, ah, bugger. Yeah. What's he doing here? Yeah, h nu minus that, and then it does that, and he's not using that, and then he's... right. Yeah. Okay, so we've got this equation up here. We'll call it equation 3. Yeah, that's the gauge pressure. And to find out the percentage increase, he's being really fancy with the maths, and he's using this as a divisor to get rid of this rho g in here, right? So let's ignore this and go back to this, and we'll call this equation 4. And what we'll do is we'll do 4 divided by 3, right? Equation 4 divided by equation 3. So what that does is gets rid of this rho g here. I hope everyone's clear on that. And what it does is it adds this h in here, and that's a percentage. That's the percentage increase, right? That right there, that equation there. And what we end up with is that being 1.5, right? So it's 150% increase in h. Okay, are we clear on that? I'm sorry that wasn't the best delivery of my, it wasn't the best delivery there. I hope that makes sense. I hope we got there in the end. We got a bit muddled. Are we happy? Are we okay? We doing okay? Huh? No, it's 75, sorry. 75. 75. Why? Because we're talking about, so up here we said that the absolute pressure, this pressure, the 150 kPa, increases by 50%. Okay, so I used this 1.5 times factor to move that up 50%, right? And then I've skipped a step, but I've taken this bar off, right? Which is, yeah. So then that brings that down to 75. Yeah, not the best explanation. Sorry, but we're all okay. We're there. Oh, what time are we on? What are we on? Ooh, okay. We've got a bit more time. So we've got one more question. There are 2 more questions, but we've only got enough time for one. So would people rather do question 5 or question 6? Does which one did people need? Sorry. Oh, did he? Oh, that's nice. Well, let's do 5 then. I don't watch the lectures. I've got other things to do. I've got robots to build, man. Right. So question 5. Question 5. We've got this dam. Wow. It's not quite as good as the beavers do, but we've got a dam, and I'm going to draw it in 3D because it helps for conceptualization. It's 40 meters wide. It's 60 meters deep, and it's 80 meters high. Not to scale, and it's got a crap ton of water sitting on it. Alright, cool. We know the density of water, we're given that. That's 1000 kg m minus 3. We're also given the concrete weight. Why would we need that? I don't think we do need that. And we're given the pressure of the atmosphere, which is given here as 100 kPa. The classic. Okay, so there's two ways to do this. When the solution sleet's released, you can see one of the other ones, but I'm going to do it using, pardon me, a similar method to what we did with the sediment, which is using the integrals, because I think it's important to understand the integral method because it's more versatile. And you'll probably use it more in your future life as engineers. Let me go to the thing. So we've got the pressure. The pressure on dam is a result of both the air and the water's pressure. Okay, so we've got the air pushing down, but we've also got the water pushing down. The air pressure is only vertical. It only acts downwards onto the dam because it's fully submerged. The water, however, acts both horizontally and vertically. So we need to split it into two to deal with it, right? So what I'm going to do is I'm going to first start by doing the horizontal pressures. So horizontal pressure. So this is the pressure coming from the water over here, okay? The horizontal component. So we can write that. We're asked to find, let me be clear on what we're asked to find. The pressure force, right? The force from the pressure on this dam. Okay? So we can write this. The force from the horizontal water, so that's what that subscript means, horizontal water, is equal to it's going to be the height of this dam. So essentially imagine the square of this square here. That's what's getting pushed on. This is the horizontal component, is that square, right? But it's kind of bent. We're going to sort the bending out in a moment. So that's, again, it's that integral. So we're adding up all the little chunks down the height of the dam. And we're going to write rho dA, right? Rho dA. So that's saying density over every little chunk of area of this. So we're essentially dividing this up into little tiny squares and asking what is the pressure in each of these little squares and adding them all up. Okay, does that make sense? We okay with that? That's what integrals do. And then what we can, wait, there should be, I think there should be a G in there. Yeah, there should be a G in here. Right, and then we're going to expand out this dA bit, right? So I'm going to write that as rho, that's the water's density, G, and then that's H times the height times the width, right? So that's just defining this whole area here, because this is the width, and that's the H. And we're going to differentiate that with respect to DH, so as we move down each little bit, all right? We're going to go down each little bit. So what we're going to write after this is we're going to put in, that's 40 from, oh, that's the width. So this is just 40 and it's a constant, so we can move that outside. Same with rho, the water and G, they're all constants, so we can move them outside of the integration. Literally just like we can write this as rho G W and then the integral H dH. And that means inside we get this. Cool. Okay, so that's what we end up with there. If you put in 8 squared and all that loveliness and times it by the 40, you end up with this big boy number here, rho WG. Okay, so what we've done there is we've essentially just said that the force from the pressure is going to be equal to the pressure times the area. And so each one of these we've divided up into tiny little areas called DAs, which just basically means an infinitesimally small area. And we're just going to add up every little bit of that area in order to figure out what total pressure is, right? So then I converted the small area into a height and a width, basically saying that you can like divide that into strips rather than small squares. Yes? Oh, sorry, what? I pointed at the other guy, but yeah. That's 128,000, yeah. What were you going to say, sorry? Yeah, so good point. It's because we're dealing with the horizontal component of the water, right? Because the vertical component of the force is going to deal with the air pressure as well. So we're dealing with both. We will do that, but in a bit, right? We're just going to get these components first. So this is a horizontal component of the force, right? So this is that bit, force and the horizontal, right? Once we've got that, we're going to do the vertical. So that's the pressure from the water in the vertical. That is equal to. Oh, it's not even pressure; it's force. Yeah, that's what we're dealing with, isn't it? So the force of the vertical water is equal to the mass of the water, gravity. That's just your F equals ma, right? That's all we're talking about there, because it's just sitting on it. And we're going to say that the mass is equal to the density of the water times the volume of the water, g. Okay? So then we're going to write rho wg, and then we're going to write, what have I written there? The volume of the water is this whole chunk here, isn't it? So it's the same as the dam but inverted to create that square. So it's from this point up to here, over to here, down to here, right? That's the chunk of water that's sitting on top of the dam, and that's what's going to be contributing to the force in the vertical direction on the dam. Okay? So we need to figure out what that volume is. So that volume is given by 40 times 80. So the 40 is the width, this is the width, this is the height, and then we've got 60 over 2, which is the B to C, this bit here, but going up there. It would if you were to do it like without the divided by 2, it would define a square, and you know the equations for triangles. You're smart kids. Yeah. So then when we put the numbers in again, we end up with 96,000 rho wg, right? So that's just all these numbers being times together. Okay? Are we happy with what I've done there? Yeah. Just to recap, we've said that the force from the water in the vertical direction is that volume of water sitting on top of the dam. So all we've done is we've used F equals ma to do, and A here is g because we're talking about gravity, and we've used that to calculate our force. We've noticed that mass is just density times volume, so then what we've done is we've calculated the volume of water that's sitting above that, and used that to create this algebraic expression there for the force. Okay? Happy? Any questions? Alrighty. I'm trying to finish up as fast as possible. I know people probably want to go home. So the force of the air, well, the force of the air is. Why is it like that? That is interesting. Ah, right, yeah. So the force of the air. Let me draw the dam from the other side for you guys. So the force of the air in the vertical direction acts like this, right? I'll draw some arrowheads. Yeah, it acts on the whole slope going down, right? Rather than just like on the square, it's acting on the slope. Okay, so that's the force of the air and the water, actually. Sorry. So in order to calculate the force of the air, we need to do the width, which is this bit, and then we need to figure out what the size of this square is. So that's 60 plus 80 squared. 60 squared plus 8 squared. That's to figure out what this length is here, right? We'll call that the hypotenuse. This is the hypotenuse. Yeah. So we're saying width times hypotenuse gives us this square here, the rectangle here, and that's what the air's acting on. And that times by the pressure of the air, because it's pressure, remember pressure is an area, affects the whole area, so to get the force we need to times it by the area. That gives us 1 times 10 to the 5, 1 times 10 to the 5 times that, which gives us